Much, Christian. Good morning, everyone, and thank you very much for inviting me. And I'm really excited. It's a pleasure and honor for me to present our recent results and see also the attendees from all over the world. So I will talk about. Probably I should go to the play mode. I'll talk about our recent progress and recent thoughts about nuclear many-body problem.
It's like, oh, it's okay now. It's always Sherry.
That's not me. Nuclear many-body problem with an accent on emergent phenomena, because I think it's important. Especially when we talk about the accuracy of description of nuclear spectra and related quantities. So in general, emergence is very well known, not well known, probably not well understood, but known property of interacting many-body systems. And when we speak about emergence, we mean drastically different behavior of the entire system, which originates from collective behavior and interaction of the constituent local degrees of freedom. Remarkably, the emergence is associated with resolving conceptual difficulties in various contexts, in QCD, in amplitudes, in condensed matter, in understanding superfluidity and superconductivity, and of course, in nuclear physics. And understanding emergence in one area would probably have a broader impact on other areas. Answering big questions at fundamental physics frontiers by extensions of the standard model, for example, to include gravity, and connecting explicitly the ultraviolet and infrared physics, reveal the emergent character of space-time, and that highlights the fundamentality of emergence. That's why we pay special attention to it. For the strongly correlated many-body systems like nuclei at low energies, basically, we speak about computing emergent degrees of freedom from an ab-initio Hamiltonian. That would be my definition, my local definition of understanding emergence. And this will be linked here in the formalism to the interaction kernels of the equations of motion for correlation functions. As an example, how emergence can manifest itself in atomic nuclei, I would mostly focus on collective motion, but there are also clustering, shell structure, and other phenomena for which emergence is responsible. I will show some examples of how can this happen, some examples of nuclear spectra and reaction rates in astrophysical environments. So let me start with the general Hamiltonian. It's given here in the simplest form without sophisticated three-body terms and in non-relativistic form also. But what I will be saying is quite general and can be generalized to more general Hamiltonians or more specific Hamiltonians. When we talk about single particle motion, we introduce the single particle propagator, which is given here in terms of the field operators. Why is it interesting and why is it convenient to work with? Is because its spectral expansion is connected directly to the observables. For example, the poles of the single particle propagator define the energies of the neighboring odd system. If we start from even system, both odd systems and the residues are related to occupancies or spectroscopic factors. Talking about higher rank green functions or propagators or correlation functions in this context, this will be the same notion. Another important quantity is particle Hall response, and that's the propagation of particle Hall configuration on the background of the n-body interacting system. And we'll be talking about fermions, of course, here. And again, the Fourier transform has a simple spectral expansion form where excitation energies are defined by the poles and transition densities, which characterize the probabilities, and the excited state wave functions are the residues. The general equation of motion formalism implies taking the derivatives with respect to both time variables, and that's how we arrive to the Dyson equation for the correlated single particle propagator. Here it is shown after the Fourier transform. So the Fourier transform of the two-point function is just one energy variable function that's in the energy domain. So G0 is the free motion propagator, and the exact self-energy is decomposed into the static and energy-dependent part. So I want to emphasize that this is the exact result. This is derived from the underlying Hamiltonian. This is no approximation. And again, we can also put here the exact form, in principle, exact form of this interaction kernel, which is also called self-energy. So here is the algebraic and diagrammatic form of the static part that has a Hartree-Fock ansatz, although contains the correlated density, and the time dependent or retarded or advanced, that's why I put an R typically here, is again a combination of commutators, and it's given here on the right. So it's just a convolution, double convolution of the three-body propagator, namely two particle one Hall propagator here with two matrix cell modes. So everything is in principle defined by the Bayer interaction, that's V bar, anti-symmetrized Bayer interaction. This is the only input. Solving such an equation is not so simple, of course. First of all, this three-body propagator has to be determined in some way. And then it gives also the feedback on the density in the static part, because actually the density is the static limit of the propagator itself. So it's highly nonlinear. And the methods which I'm explaining is also known in principle for ages, for decades. And now I want to discuss possible ways how can we treat this 2-point 3 fermion green function. So the direct generation of the equation of motion for it would lead to a similar equation of motion with a static and dynamical kernel. However, it will generate higher rank correlation functions and so on. So you can continue until your particle number is reached. That's sort of equivalent of the famous BBG-KY hierarchy. But we can treat it approximately, for example, like presented in this paper from 1973 by Peter Schuck, Peter Ring, and collaborator. You can just solve an RP equation for it without putting any dynamical kernel. Alternatively, there is Watson-Faddeev type series for the vertex that's discussed in the work of Pavel Danilevich and Peter Schuck. Or you can do the so-called cluster decomposition of this function. That's also in principle known technique from Martin Schwinger, and we particularly follow Nicole Weinman proposal how to decompose this. So this is already the irreducible part. So basically you drop the three-body correlations, the genuine three-body correlations, and reduce the propagator to one body and two-body correlation functions. This is shown diagrammatically here. So this is the approximation. However, you keep the, as we will see in the following, the most important effects by retaining these correlation functions. Here, there are particle-particle and particle-Hall correlation functions. And remarkably, this can be exactly mapped to the following terms. And the mapping is shown diagrammatically here. So you can associate those constructions where there is a correlation function in between two matrix elements with new vertices and new propagator. And this is, again, this is exact. So this is done formally here. So we see the formation of sort of new particles. Sometimes we call them quasi-bound states of particle-Hall or particle-particle, or we call them phonons. Yeah, this can be also generalized to superfluid case, because in principle, you see there are two types of phonons. Here, one is a particle-Hall, the other is particle-particle, and they form, they can be combined in the superfluid formalism, for example, in the space of Bogoliubov quasi-particles in one object. This is shown here. This would be then the retarded part of the self-energy with all types of phonons. That's how they combine to one structure. And actually rotating in this Bogoliubov space, this self-energy takes a very simple form, just one term having two vertices and a propagator in between. That has to be calculated in quasi-particle space. Another interesting consequence of this is that actually you can see that you can rewrite your Hamiltonian in terms of effective degrees of freedom. So instead of having fermions and Bayer interaction, you can now have, instead of this Bayer interaction, you have the phonon exchange interaction, and phonons emerge as new particles, the bosons, which can only exist in the medium. So this is the effective Hamiltonian, which is known also from the quasi-particle phonon model of Solovyov and nuclear field theory of Milano, Copenhagen group. However, this was not usually derived. This was more like postulated or derived from effective interactions. And I think this is a really interesting feature of those emergent particles, because you actually see that you generate the vertex of the type or usual boson exchange vertex. For example, you can compare it to the elementary interactions in the standard model, where this boson exchange interaction is introduced as an input. But actually, from all this construction, you can see that whenever you find the boson exchange interaction between the fermions, there can be some underlying theory. So now I will move to the response function, because the results I'll be showing obtained for the response. However, just to mention here that we also investigate the single particle motion in various contexts. So the equation of motion for the particle response can be found similarly. Again, we just differentiate this correlation function and then make a Fourier transformation to the energy domain. And that's, again, similar equation of motion. So we call it Bethe-Salpeter-Dyson equation, because it's certain limit of the Bethe-Salpeter equation, the limit of two-point function, and it has a Dyson form. And again, there is a free motion here, and there is a all in medium physics sitting in the kernel that has both static and dynamical parts. And these are shown diagrammatically here. So we have a mathematical derivation of both, but just to make it more understandable, I put it in the diagrammatic form. The instantaneous term is sometimes called bosonic mean field. This is widely known from the studies of Peter Schuck and collaborators, and this is part of the self-consistent RPE approaches. So here basically we have all possible contractions of the interaction and two-body density. So rho here is a two-body density, which is in principle related to the static limit of the response. So again, we have a similar situation of nonlinearity. And again, there is a time-independent or dynamical term, which has a higher rank propagator. So basically here we have G4, it's always the rank of n+1 if you start from n body propagator, if you want to have a symmetric kernel. So it can be written differently with non-symmetric kernel, then the rank is 1 unit higher. But we find that actually having these kernels in symmetric form is more instructive. So here you see this G4 is constructed in all possible ways with two metric summits of the Baire interaction, which produce our four-pole function. And again, there is a problem how to calculate that. And there are various strategies also known from quantum chemistry, for instance, and condensed matter physics. This is actively investigated in that areas. I will consider here one term from the kernel shown above. The term where we have this type of contraction, and for the other terms it will be similar. So basically we have to find a treatment for this for fermion correlation function. So it can be taken in just fully uncorrelated form. This is just symmetrizations, anti-symmetrizations, and in this form, I think you produce second RPE. Another possibility to have a correlation between two particle lines, any two particle lines and have a free propagation of the other two. So again, we list here the possibilities with particle Hall and particle-particle correlation functions. And there are some additional anti-symmetrization terms here. And finally, you can have correlation between each pair of lines, which actually looks much simpler. Yeah, in this way, we drop 3-body and 4-body explicit correlations. However, keep the important 2-body correlations. So we can call it conditionally truncation on the 2-body level. Why is this special? Because we can close truncate this infinite or large hierarchy of equations and have a closed system of equations. Yeah, actually, if there are questions, you can ask me right away. So if there is something unclear, can repeat or stop. Again, we can do the mapping similarly, and we found out that actually having this second approach, we can map this dynamical kernel to the contents of the nuclear field theory at the phonon coupling model. So this will be the terms which are typically entering the retarded kernel of the NFT, both relativistic and non-relativistic. However, we get some instructive hints how to extend this theory, because this type of the kernel, which is shown on the right, was becoming kind of the standard one, and we couldn't go beyond that because the derivation of this was pure phenomenological. Here we have the hints how to extend that. For example, we have additional terms in the kernel with the correlation function, and in addition, we know that these correlation functions should be in principle exact, and we can iterate these kernels. So all in all, if we combine the particle Hall and particle channel in one object, so to say, one composite correlation function of rank 2, we have a closed system of equations with the kernel, which depends on this external, depends on the G, which is the quantity that we look for itself. Now about the interactions. Of course, there are now very, very good interactions available, such as chiral interactions and meson exchange interactions. We haven't yet, I just wanted to emphasize, we haven't yet implemented the full many-body scheme based on the Bayer interaction. And this is actually the ongoing activity. Instead, in the calculations that I will be showing, the interaction is taken the effective form, which is adjusted to the relativistic mean field. On the relativistic mean field level, let's say, to the properties of characteristic nuclei throughout the nuclear chart. This is the whole idea of the relativistic mean field, originated from Sirot and Valechka, and we largely use the input from the group of Pittering. And yeah, actually there are techniques which we call subtraction, a very simple procedure that we should perform if we use the effective interactions, that eliminates the double counting of this emergent phonons from the effective interaction. So this is schematically the equation that we solved, the equation for the response function. It has three parts. It has the static part, which, as I said, we take now in the form of effective interaction. So we don't calculate this double contraction, this single contractions with the two-body density. But the dynamical kernel is more in our focus, because actually the static kernel is mostly responsible for the renormalization of the interaction, and the dynamical kernel is responsible for the structure of the wave function and fragmentation effect that we see in the resulting spectra. This is the subtraction that I mentioned. This is proposed by Viktor Tselaev already about 10 years ago, and this is used now in calculations with different effective interactions. So the conventional nuclear field theory kernel is shown here again, just for the reference. And then we will be comparing calculations with conventional kernel and the extended kernel here, where we introduce additional correlations between these fermionic lines by iterative procedure. So first, we calculate by the relativistic RPE, we calculate the phonon characteristics, which actually come out very nicely just because we are using effective interaction. So that's why we don't need complicated iterations. We can enter the cycle with realistic phonons. So we calculate the phonons, then we calculate this response function with the conventional kernel. And then on the third step, this response function is entering back the kernel. And then the procedure is repeated. So basically, if you do this two iterations, you have the processes which are shown here in the right bottom taken into account without evaluating this complicated diagrams. That's the advantage technically. Let me start with calculations with an NFT kernel just to illustrate how they affect the accuracy. These are calculations of Caroline Urban for the Gamow-Taylor resonance in the nickel chain. Nickel neutron-rich nuclei are shown here from nickel 68 to nickel 78. And here you just see how the dynamical kernel changes the calculated spectrum. So blue lines are obtained with relativistic QRPA, proton neutron, and the red are obtained with dynamical kernel. And the RQTBA is the abbreviation of the approach, relativistic quasi-particle time blocking approximation. Basically, it means that we include the NFT dynamical kernel with the phonons. So yeah, it shows really strong fragmentation, and we know actually that the low line part of the Gamow-Taylor spectra is responsible for the beta decay rates. Beta decay rates can be extracted. So here, Caroline gave the more detailed spectra in this beta decay Q beta windows with fine resolution. So the color code is the same. So you see that there are differences between them. Between the strength, considerable differences, and I think there is another calculation here, which is also performed with dynamical kernel, but not fully separated phonon space. So, but basically we have to compare red and blue. And here are the cumulative sums. So this is the formula for the half-life, and here's the result for the beta decay half-life, these isotopes. So you see that the difference is really substantial, and having this dynamical kernel is important for reproducing the beta decay half-lives. So I now move to the effects coming with the higher order configurations. I will call them higher rank configurations because it's not really clear what's the order parameter. Often we associate the order parameter with this quasi-particle vibration coupling vertices, but there is no good power counting rule here. So I'll say rank. So three models are compared here for the giant dipole resonance in calcium isotopes. One is open shell, the other is closed shell. Black is again the simplest calculation with QRPA, relativistic QRPA. Only two quasi-particle configurations are taken into account, and only the static kernel. Blue is our time blocking approximation quasi-particle with coupling to one phonon, and red is the iterated kernel, which is shown here. So we see that actually the difference between model 1 and model 2 is more noticeable than between model 2 and model 3. And this is a good sign because we have kind of a saturation of this high rank effects. But still, the difference is important because if we compare it to experimental data, we see that we can better describe the giant resonances at least above the neutron emission threshold. So here is another calculation for nickel 68. This is for pygmy dipole resonance. We had very interesting data from Oliver Wieland on the low line dipole strength here. And again, we can compare three approaches the same. I think this is below threshold, so we don't have continuum, but we put the resolution of the smearing of the strengths similar to that of the experiment. And we see that we can, in principle, have an improvement of the description by going to by including this type of correlations. Here's another example of the low-lying dipole strength calculations. Again, we had very good data. That's why we wanted to see how the approach performs. Actually, in this energy region in calcium 48, there is no dipole strength in QRPA. So if you do QRPA calculation with only static kernel, there are no states. So we only compare the calculations with two less complicated, more complicated dynamical kernels here. And again, we see sort of improvement compared to experimental data with this approach, which is, has a long name. Shortly speaking, with a more complicated kernel with emergent effects. And accuracy is better, but it's not ideal yet. And while doing all these calculations, I'm always thinking, where do we stop and how we continue? Where should we go? And some of the thoughts are written here. Do we really believe high rank configurations produce high accuracy? In principle, the calculations are very limited, but they point out that yes, but how can we really quantify that? How accurately we can describe the spectra in principle? And we looked at the experimental data. There are very, very accurate data. However, there are not good standards for the theory. Typically, we are asking about 200 keVs. Can we, for example, reproduce the spectra with this type of accuracy? That's what I was showing for nickel. And of course, the more accurate, the better. But how is this related to configuration complexity, for example? This was never discussed. And here, I just found out that in chemistry, in quantum chemistry, they have the notion of chemical accuracy that's well defined, and it's achieving that is possible with certain type of calculations, namely the couple cluster calculations up to the they call it triples, but basically this is 3-particle 3-hole configurations in some included in some non-iterative way. So yeah, what I was showing is also 3-particle 3-hole configurations, although with effective interaction, but still we see that we do not reach the accuracy we desire.
35 minutes, Elena.
Okay, thank you. So probably this is the nature of the nuclear forces, because they are not weak and they are known with limited accuracy. But likely there is also something about the many-body methods. And actually working with model Hamiltonians, which have exact solutions, can allow one to focus on one issue only. We can eliminate the complications related to complexity of the interaction and work with simple tunable interaction. And this working with such Hamiltonians is also now interesting in the context of developing quantum and hybrid classical quantum algorithms when they exist in noisy intermediate scale quantum devices. That's why we try to formulate the problem in that context. So we took a 2-level Lipkin Hamiltonian that's written here without the W term, just to begin with. So it's very well known and very well studied Hamiltonian. This is written in quasi-spin operators. And then what we wanted to do is to calculate the ground state and then apply the excitation operator, which allows us to vary the complexity of the excitations and see how changing configuration complexity can affect the accuracy. And the algorithm we used is the variational quantum eigensolver. That's in the implementation I will be showing. It uses the couple clusters and that's, and then we also borrowed the existing quantum equation of motion algorithm from quantum chemistry calculations. So first we applied the VQE on this Hamiltonian, which is in principle known procedure. Although Mankoba, who is leading this project, our PhD student, he discovered together with other young collaborators that we are having in the group an efficient encoding scheme. And then the QEOM method generates the equation of motion matrix by calculating these commutators. And finally, we diagonalize it. So I just some preliminary results just to make to give you an impression how it works. So we did calculations for different particle number. And the task was to see how the accuracy varies with the particle number, configuration complexity, and interaction strength. Because actually what we see in all cases is that the strongly coupled and weakly coupled regimes are very different. For example, we get more noisy results. And that's something to analyze in the future. So you can compare two implementation schemes for n equals 3. So that's how we picked the optimal scheme. Actually, this is called G scheme, the total spin basis, the more efficient encoding. And then we applied for higher particle number. So basic observations are kind of expected. But now we can quantify that. So with higher rank excitations, you have better accuracy that's demonstrated here, stronger coupling, more noise, and then more particles, again, lower accuracy and more efficient implementation, higher accuracy. And nice thing is that we can do it also in simulator in classical device, and we can eliminate the effects of the noise and get the information about how the complexity of the excitation operator is related to accuracy. So this is work in progress. I cannot give more now. I'll just move to the finite temperature calculations for the rest of the talk. This will be just a couple of minutes, I hope. Just to see how this, to show you how this emergent phenomena that come with the dynamical kernel manifest themselves in astrophysical reaction rates. This is schematically how the generalization is done for the finite temperature. Instead of normal averaging, we have thermal averaging for all the correlation functions. And by a similar time blocking technique or just by the equation of motion, we arrive to similar equation. And again, a similar kernel of the NFT type comes out at finite temperature. It has a little bit more complicated structure, more terms because of the thermal unblocking, and some additional dependence on the fermionic and bosonic distributions. This is one calculation that we did for calcium 48. And here I just wanted to illustrate how it works for the gamma-stellar resonance. So this is the calculation in the finite temperature relativistic RPA. This is with the dynamical kernel, relativistic time blocking approximation, with relatively large smearing. So this is now just showing how the overall strength evolves and how the fragmentation pattern evolves with temperature. Here are calculations with small smearing that we can see individual states. And here, well, we're still discussing about the subtraction, how to do that in the case of the gamma-stellar resonance, because pions are not entering the fitting procedure for the effective interaction in the covariant density functional theory. But just a curious case that we obtained, I wanted to show it, that it can actually happen that at zero temperature you have no states in the Q-beta window, which means that the nucleus is stable, but at finite temperature, especially if there are first excited states close to this borderline, can become beta unstable at finite temperature. So this is still under discussion because we have no good, we don't have a good, well-defined procedure of the subtraction. But just a possibility. So more calculations we did for the waiting point nuclei. Here are nickel 78 and tin 132, gamma-Teller resonance and spin dipole resonance that's responsible for the first forbidden transitions. And again, that's just overall picture of the gamma-Teller and the low line strengths. So here is how it evolves with temperature. And this is exactly the strength which we use to extract the big decay rates. Also here, so first forbidden contribution is smaller, or in most often, but there are certain cases it can be large. So this is summarized here in the right bottom. At certain electron density in thermodynamical conditions, we call it overall temperatures and densities, combinations of temperatures and densities. Here are the rates, the half-lives at zero temperature. We can benchmark the experimental data, and this is how they evolve with temperature in both approximations. So yeah, the numbers here show the relative contribution of the first forbidden transitions, which, as you see, can be sometimes important. Yeah, the last example I'll show is the application to the electron capture rates, also in the under some typical thermodynamical conditions. So two densities are put here, lower density and higher density, and two approximations that we use to calculate the GT plus response and to extract the rates. So how we extract the rates shown here. This calculation does not have first forbidden contribution, but nevertheless, we wanted to see how this emergent performance from the dynamical kernel affect the rate. So you see the differences can be really large. That's the differences between blue and red. And we compared those schematics, which are largely used in the simulations. So that's the schematics from Lagrangian and Martinez-Pinedo. And actually, that's something for the moment. That's something to think about. How do we proceed further? Do we include more correlations? Do we include first forbidden? And whether we probably develop some alternative parameterization for those rates. So summarizing, we have now the nuclear field theory in relativistic framework. It's formulated and advanced in the equation of motion, a framework with the emphasis on emergent degrees of freedom, which renormalize interactions in correlated media. They underlie the spectral fragmentation mechanisms and affect superfluidity and big decay rates and many other characteristics. The accuracy of description is linked to configuration complexity, interaction strength, and particle number via the studies of solvable models. Then we generalize the response theory to finite temperature and apply to the different excitations. And we extracted the weak rates at astrophysical conditions and showed that correlations beyond in field are significant. So current developments are deformations, and had relatively recently a talk about this. Then we work on, we are thinking about how to implement the obtained weak rates into simulations. Basically, this is thinking about large scale calculations. There is a research direction toward ab-initio description. So we're working on the static kernel and see how this can be calculated from bare interactions. Superfluidity is receiving a special attention because we found that also superfluid pairing in astrophysical conditions shows some interesting properties, and this is needed to extend the application range at finite temperature. So we look at efficient algorithms, and the quantum computation is led by Mankoba Lachwar, our PhD student. And yeah, for the perspective, we consider relativistic formulation, a bosonic equation of motion, and probably applications to neutron stars. So there are many possible applications of the formulas. So I would like to thank my collaborators, my young collaborators from WMU. Herli has moved to Taiwan. Caroline is now in Germany. So many thanks to them. Peter Shuk, Peter Ring, Tamara Nikshechan, my long-term collaborators, many thanks to them too. And I acknowledge our funding from NSF. So here are some pictures how the group was changing over the years. So, and thank you very much for your attention.
Thank you very much, Elena. That was a nice talk. So please feel free to raise your virtual hand and ask questions, or just type it into the chat window. Just to break the ice, if there is ice, let me get started with a question. So I'm in general interested in solving the Dyson equation perturbatively, and you showed lots of many-body diagrams, and I was wondering whether you derive those by hand, or can you sort of auto-generate those?
So this is exact. So this is just exactly, you work out the equation of motion and you obtain this. There is no approximation. You don't need perturbation theory for that. You don't need any machinery.
Right.
But
exactly.
then, yeah. And then, yeah, as I said, what we do, we develop some approximations to this.
So, but later you showed a diagrammatic expansion, right?
Yes, this is the approximation which we use.
Exactly. I mean, do you do this by? I mean, do you write those diagrams down by hand, or is there some clever way of?
So this is done analytically.
Those?
So this is done analytically. We don't use the diagrammatic technique. I only use diagrams to illustrate the results. So what we use is shown here in the bottom. This is called cluster decomposition. You assume, well, that's the general principle of QFT. So in order to have at long distances, you have your particles free. Basically, that's the idea. So you drop what we drop here. We drop here the fully correlated three-body effects. So this is not included, and this is the only approximation here. So you retain, so to say, exact. In principle, it should be exact. Correlation functions here. These are which are called R capital, particle, 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 whole, and well, there is perturbation theory term. Basically, it can be included, or usually we assume it's small. And if you have strong coupling, this is the lowest order term. The high order terms should be more important than the low order. And these correlation functions are calculated separately. So they are external to this Dyson equation. So for this correlation functions, we solve the two-body equation. So this is a coupled system of two-body and one-body.
Okay. Thanks, Elena. So are there any questions from the audience?
Yes, I had a question.
Oh, yeah, go ahead, please.
Yes, my question is, when you write down all these diagrams, you need interactions in between. So what type of interactions do you use here? Is it just the second derivative, or at one point you
well,
said you are exact, you would have the bare interaction.
in principle.
In principle.
Well, yes, the problem is that in order to derive this all the content of this many body theory, we need to start with bare interaction. Because if you start with effective interaction, we are lost. I mean, it's not really a clear procedure. So we derive it from bare interaction, but then for the implementations, we replace it. I mean, for now, we replace it with effective interaction. So you replace this entire block here with effective meson exchange interaction.
Yeah, I understand that. So you know,
what
but there is a danger of double counting. And
yes, that's why we have.
That's why I've showed that. Do you have a similar mechanism here as this what I've showed in RPA?
Yes, exactly. That's what I was writing here explicitly. So we use your covariant density functional theory for the static kernel, and then subtraction that was here, subtraction of the double counting in the dynamical kernel. Well, actually, you see that this plays a role, since this is not energy dependent, plays the role of normalizing this V term here. So the short answer is that yes, if we use effective interaction that's adjusted to finite nuclei, we have to do subtraction.
Okay, thank you.
Thanks. Any other question? So in the section about finite temperatures, so you showed one figure or set of figures with the temperature. I think it was 1 and 2 MeV. So why did you, or 5? Or let's say 2. So why did you stop at 2 MeV exactly?
Here, yeah, up to 2 MeVs. That's the typical range of temperatures that we have in. Well, that's what I heard from my colleagues who are doing supernova simulations. Maybe up to 3. Well, it depends on the nuclei, but that's the typical relevant temperature range.
Okay, so you were interested. So this is okay. So you were interested in the physical range rather than some technical limitation, right?
Yeah.
So in principle, you could go way higher than just 2 or 5 MeV, right?
Yeah, we have calculations with crazy temperatures. This was in our paper. Yes. Just to push to the limits to see what happens at very high temperature. These are very high temperatures, basically at the limits of nuclear existence, I think. And we see this interesting phenomenon when the low line strength blows up and the giant resonance basically disappears. But it does not happen at temperatures which you have in the stars.
Okay.
That's why I didn't focus on that.
Okay, so any further questions from the audience? Okay, the chat window is empty. Okay, then that's it, I guess. Thank you so much again, Elena. That was quite interesting. So our next speaker is going to be Baha Balantekin in 2 weeks. Unfortunately, the title is still TBA, but I think it's going to be very interesting. So I'll see you in 2 weeks, I hope. And once again, Elena, thank you very much. Best regards to you and also Yinu, and see you around. Bye. Thanks.
See you. Bye.